I have 35 total, yeah, and it's my responsibility to listen to questions. I still not knowledge of one away. Honestly, I was just thinking that Nathan coming from another he just yeah, well, all right. Since his talk is in the afternoon, he will arrive in the morning. Yeah,
He's calling. You should know that. Met him like 4 times.
Morning, everybody. Welcome to day 2. Thanks for coming.
You don't mind better next time.
Today to start, we have Krastanov and Zack.
Hey everyone, the microphone's working. Thank you for inviting me. I've grown to really appreciate these smaller workshops. I, at least for myself, get a lot more value out of them, being able to talk to you folks than from the big conference.
Light on?
The red is not on. Test.
You're on a mic.
So I will be presenting. I'll try to present something that goes over a lot of background about more recent styles of constructing error correcting codes, and the second half will be mostly work done by one of my graduate students. I will be hand-wavy and abusive with some math notation from time to time, just to try to speed this through. But please feel free to interrupt me. Don't hesitate if you stump me with a question on the math. But I guess the whole point here is to be able to interrogate these constructions. So a little bit more about my team and the UMass team as a whole. I work at the CS department at UMass. Also, my background is in physics. A lot of the work we're doing with the faculty there is focused on quantum error correction at the architecture level, systems level question. There's a lot of work happening on quantum networking, especially as part of the NSF Center for Quantum Networks. And I personally also work a lot on scientific software. I try to contribute to the open source ecosystem and also to do some of the community work needed to build that system of volunteers, really. Some of the bigger tools that we're supporting is a package for intricate Clifford algebra and construction of error correcting codes, and also as part of the NSF Engineering Research Center for Quantum Networks, and as the part of the National Virtual Quantum Lab, AspenNet, I'm working on a network simulator that's used for their virtual testbeds. All of these is very open developments. And in terms of community building, if nothing else, I would really like to advertise the summer school we're running in numerical methods. It's been funded for the NSF for a few years now. For $90, a student gets room, food, and 8 hours of pretty intense lectures on numerical methods for a whole 5 days on our campus. And our campus has been winning best college food for the last 8 years. So that's also a reason to come in over all of the US. Yeah. Anyway, back to the actual topic of the talk today. I'll be talking about a particular construction for error correcting codes that ended up being very general, very convenient for searching for error correcting codes. A lot of this work, the majority of this work was really done by a graduate student of mine with support from me and from a colleague at the math department. So I'll start first by trying to discuss how we've started building good classical codes over the last few decades, how we've tried to use similar techniques to build good quantum codes, and in the last few years, what has happened that has precipitously changed the overhead we would expect from quantum error correction by really many orders of magnitude. Like 5 years ago, I personally was a little bit uncertain how soon a fault-tolerant quantum computer would exist, but the astronomical progress in error correction of the last 4 or 5 years is really, really encouraging. And I want to talk a little bit about that. So to have a good classical error correcting code, we usually say that we don't want the rate to be vanishing. We want a constant rate. We want the distance to scale with the block size, not to get lower and relatively speaking lower. And we want a good decoder, that it's efficient when doing some form of approximate maximum likelihood estimation. That's not given a priori. Maximum likelihood estimation, decoding in principle is an NP-hard problem, but for certain structures that are added to error-correcting codes, you can get much more efficient decoders. And really for classical codes, there are a little bit more requirements. That field is a little bit further along. They're really strict about actually getting all of the rate you can get out of your code. But we won't talk about these details. And to get a good classical code, it's actually pretty easy. Just pick your favorite programming language, generate a sparse binary matrix in it, and that will probably be a good classical error correcting code. There are some caveats about, well, make sure that you don't have rows or columns with zero weight and so on. But with very minor post-processing, 1 or 2 lines of code, you can get a good classical error correcting code. The issue is, why does this not work when we start doing quantum error correction? For quantum error correcting code, naively you can think of a big family of quantum error correcting codes that's really just built out of 2 classical error correcting codes, one to check for Z errors, one to check for X errors, but these need to be consistent with each other. The X checks and the Z checks as measurements need to commute because you don't want measuring the stabilizer for one of the checks to destroy the code state with respect to the other check. So this commutativity can be expressed in terms of a very simple constraint equation between the 2 parity check matrices. The parity check matrix for the Z code times the parity check matrix, the transpose of the other parity check matrix needs to be equal to 0. These are binary matrices. So the reasoning here is that an X check and a Z check need to match on an even number of qubits so that they commute. But if you just try to sample classically, if you just randomly sample for good codes like you do for the classical codes, you don't get very good results. You can get very easily a very good code for the Z check, a parity check matrix PZ. That would be just a random sparse matrix. It would be a good code for against that type of errors. But to find a compatible parity check matrix for the X code is difficult. Especially it's difficult to find a good one. It's relatively trivial to find a parity check matrix that fulfills the constraints of commutativity. But for the same reasons that the inverse of a sparse matrix is not a sparse matrix, this easily found error correction code for the X checks will not be a good code. It would be a dense matrix, it would have high weights, the naive approach just doesn't work. So there has been a lot of history on trying to find better representations for a better data structure from which you can sample. So 2 big approaches over the last few years have been the approach of using expander graphs and the approach of using chain complexes. And I'll go briefly through both of those. Yes?
So could you specify the conditions on PX that you want clearly so that...
all the conditions I want is really this.
Well, but it's like a linear system of equation in binary space, right? So
yeah.
So you could solve it, as you said, but there are some conditions that you imply.
Yeah, you want the matrix to not be square. You set some rate, for instance. You want the number of rows to be smaller than the number of columns. You set some inequality about those sizes so that the rate of the code is a useful rate. Here I'm making very minimal constraints here. I am not saying I want to find a good code. I want to find a code that is at least a valid quantum error correcting code. That's a very low bar I want to pass. And if that's my bar, the matrix I get won't be a good parity check matrix. Won't be sparse, for instance. Won't be easily decodable.
But I guess why to compromise? Like, can we specify the conditions for the best code?
That turns it into a difficult problem.
Okay, but what is it?
I'll be hand wavy for a little bit. I want to pick a rate, for instance, and if I have already picked a rate for PZ, and I want the rate for the overall code to be fixed, that would give me the shape of the PX matrix. I also want the PX matrix to lead to a code that's easily decodable. That would mean that I want the row weights to be small and the column weights to be small. I want also for that matrix to be actually of independent rows, so that I don't have redundancy in it. And with that, if you can get that, you probably will have a reasonably useful code. But even that is a non-obvious problem. Enforcing that px times pz transpose is equal to 0 when you just fix the sizes of these matrices and pz is sparse and you just want px to be sparse and that's it, to my knowledge, that is a non-obvious problem.
Could it be solved by quantum annealer, for example? Because
I don't know. I just don't know. But that would be fun, using a quantum computer to make better quantum codes.
Quantum annealer to get better codes. Big difference.
Sorry?
Quantum annealer to get better codes. It's a big difference.
I didn't get that.
Never mind.
Oh, sorry. So the whole point of these better representations is that they're adding some structure to how you're sampling, so that sampling from that structure gives you for free a px and a pz matrices that are good matrices. One approach is to use a particular construction related to expander graphs. I will not cover this one, I'll just mention it briefly. Another approach is to use something called chain complexes, and that's something that I'll cover in much more detail. And it's a very rich way to impose the constraints you care about and almost for free to get good matrices sampling randomly. Good matrices that have this consistency constraint between them. So just briefly about expander graph codes. I mean, the whole fact that random sparse matrix is a good classical code is already really surprising on its own. It's related to fairly deep results in or conjectures in computational complexity. It's related to the belief that P and BPP are equivalently powerful classes. It's related to the fact that random graphs are very tree-like if you look at them locally. There's a lot of really fun mathematics behind this field. None of it is something I'll be discussing. Important point I want to make is that these were the first constructions based on this type of expander graph constructions that gave us at least asymptotically good quantum codes. For the first time, about 3 or 4 years ago, we had asymptotically good explicit constructions for quantum codes, provably good ones, where you start with a few parameters and you can prove that the construction you have will have good rate, good distance, will be easily decodable, will have low weights, and so on. The issue is that if you dig deep in the appendices of these papers, you see that these inequalities work when you have about 2 to the 50 qubits. But over the last few years, if you just relax the desire to prove that the code is good, these constructions also were used to do actual useful size codes. But nonetheless, I would say these are really good for proving theorems. They're not necessarily the best construction for practical engineering sampling of good codes. The rest of the talk would mostly be on this other construction, the chain complex construction. I'll spend maybe 10-15 minutes trying to do a tutorial on what is a chain complex, because while the notation looks very fanciful, it ends up being a relatively simple construction. And then I'll just go through the engineering steps you take to find good codes. None of the codes we'll find here will be codes for which you can prove algorithmically that in the asymptotic limit you get good rates and so on. But they will be codes for which experimentally, if you run them through a decoder or you evaluate their distances, they are practically good codes. So we're switching from the mathematics of proving things to more the engineering of getting a useful finite size code. So a chain complex is really just a chain of vector spaces, C2, C1, C0, with some linear maps between those vector spaces. And the linear maps need to have a certain property between them that we'll discuss. But this sequence of vector spaces in linear maps is all that you need to define a vector space, as long as these linear maps, which we'll call boundary maps, we'll see why, have the property that two boundary maps, one after the other, are equal to 0. The reason mathematicians started studying this type of chain complexes was because they were studying manifolds and boundaries of manifolds. So take a ball. The boundary of a ball is a sphere. The boundary of a sphere is the 0 set because it doesn't have a boundary. You don't have an edge of the sphere. Take a filled-in circle. The boundary of the filled-in circle is the peripheral circle, and the boundary of the peripheral circle is the empty set. Because again, you need to cut the circle for it to have a boundary. It's two endpoints. So that's where people started studying this type of structures, especially when they wanted to study number of zeros of a function on a sphere or existence of coverings of various manifolds and so on. And as a module of this field of homological algebra that studies chain complexes, the motto will be that a boundary doesn't have a boundary. The surface of a sphere doesn't itself have a boundary. Its boundary is the 0 set. The empty set. So I just want to give an example that's more natural to a physicist of a chain complex. Chain complex that we actually use all the time. The chain complex that teaches us that the divergence of a curve is 0 or that the curve of a gradient is 0. So if you have a scale, and here some abuse of notation creeps in. This happens to be a co-chain complex, not important. The boundary map gradient maps you from the vector spaces of scalar fields to the vector spaces of vector fields. The boundary map of a curve maps you from the space of vector fields to another space of vector fields, and the boundary map of divergence maps you from a vector space to yet another vector space. And here in this particular structure, we have that well, for it to be a boundary map, you need the property that two boundary maps applied the one after the other gives you a 0. I want to stress these are not one-to-one maps. They map some subset of the scalar fields to some subset of the vector fields. And then the next boundary map, the curve, might be mapping a bigger subset of the vector fields to some subset of the axial vector fields. So it does need to be one-to-one maps. To be fair, I'm showing this example just to give you a more hands-on example of a chain complex. We won't use any intuition relating to this chain complex for the rest of the talk. So how does this look like when we start talking about error correcting codes? Well, the main recognition here would be that the boundary of an error is the syndrome. You can think of that visually, very vividly, if we're talking about the surface code. So if you have the surface code where you have a lattice of qubits, and you have these three qubits being the errors, and I will skip making the call lattice and so on. This would be a chain. This would be a line. The syndrome corresponding to this line would be the ends of this line. And that's why minimum weight perfect matching decoders work, because they just try to take ends and figure out what are the manifolds, lines of which those ends are boundaries. So I don't know whether the people that figured out this, the utility of chain complexes were thinking this way, but alternative history I can imagine right now is that people noticed that with surface codes, we had built in so much useful algebraic structures like lattice surgery, like ways to think about decoders, ways to think about errors. And they were thinking, okay, what's the way to talk about the same topological ideas, the same ideas that something, a syndrome is a boundary of an error, without being constrained to the boring topology of a surface? Well, that's where homological algebra comes in. The structures we'll be talking about won't really have geometric interpretations. But we'll still be able to talk about boundaries of that map from the space of errors to the space of syndromes. So for a quantum code, now we need a chain complex of length 3. We want to have our space of errors, and we'll be mapping it on one side into the space of X syndromes, and on the other side into the space of Z syndromes. The way to do that is to recognize that the chain complex can go in both directions. So one of the boundary maps is relatively easy. The parity check matrix for X errors is just one of the boundary maps. It's a map that maps from error vectors to syndrome vectors. The map in the opposite direction, so the transpose of the other boundary map, is the map that maps from error strings to Z syndrome strings. Again, the reason this structure is useful is because the fact that the two boundary maps are equal to the two boundary maps acting one after the other equal to 0 is equivalent to the requirement to have consistent X and Z parity checks. And now, if you have a way to generate chain complexes, you have a way to generate error correcting codes. And we will just figure out a way for the chain complex we're generating to almost by accident to be giving us sparse boundary maps. In this structure, sparsity emerges naturally. So that's why the structure is useful. So what do we want from a really good quantum error correcting code? We want a good rate. We want a good distance. We want a good decoder, same thing that we want with the classical error correcting code. We want low weights, which is actually related to a good decoder for the classical error correcting code. But for a quantum code, it's even more important because you don't want overhead of measuring the syndrome to be expensive. And I'll add an extra requirement, which here I'm starting to actually show the contributions of my student. We also want for this code to be a single shot code. We don't want to need to measure the syndrome D times in order to fight measurement errors. We want the syndromes to be themselves error corrected in some fashion. So let's talk a little bit about this single shot. Yes?
Oh, just a question. Is there any way that you could envision also searching for codes that would have convenient sets of transversal gate operations?
A claim that my student has that I haven't deeply understood is that yes, there's some very natural addition to this structure that provides you with at least some transversal gates. I don't have in-depth understanding of what that set is. Yeah. Okay, so let's talk about the single-shot decoding capabilities. What does that mean? One way to think about single-shot decodability is the idea that the syndrome itself is a code word of an error-correcting code. So if there's a measurement error, you can detect the measurement error just by doing error correction on your syndrome. So what does that mean? Is if SZ is a syndrome, that syndrome has to be in the code space of some other code. The parity check matrix for that other code, we'll call it MZ, the meta check matrix for the Z checks. So our syndromes will live in the code space of that code, and our syndrome for the X checks will live in the code space of yet another code. So now we have classical code for the Z checks, classical code for the X checks, classical code for the Z meta checks, and classical code for the X meta checks. We need 4 classical codes that obey a bunch of relationships. Yes?
Are you saying that you need to have the meta checks for single shot, or just that it's useful?
That's one way to talk about it. My understanding is that there are other ways to prove single shot decodability. My gut feeling is that you can show that if that's the case, there is a meta check matrix, but it does seem that in the recent literature, a lot of people are figuring out how to talk about single shot decodability without explicitly constructing a meta check matrix. And again, I don't have more in-depth knowledge than that. I will be talking a little bit about the other structure that needs to be present for you to talk about, sorry, another structure that needs to be present for you to be able to talk about single shot decodability in a little bit. So for a complete single-shot decodable code, we want a chain complex of length 5 with 4 boundary maps. And we'll be discussing a way to build such a chain complex, a way that's actually so general that includes a really large universe of existing good codes already as subclasses. So the construction, for the moment, I'll describe it a little bit as a black box. The construction starts by picking a few small binary maps. You can think of them as local codes. You can think of them as something that will be parameterizing your large code. It's easy to pick a few small binary maps because we're not imposing any constraints between them. Then we'll use a black box that takes a few arbitrary binary maps and turns them into binary maps that are also boundary maps of a chain complex. That construction happens to be called the causal complex. To my understanding, and I've spoken to a few colleagues in math departments, there's nothing fundamental to the fact that the causal complex ends being useful for this construction. It's a construction that appears everywhere in homological algebra. So if anyone has some in-depth interpretation, intuition for why this complex is useful, I would love to hear it. But for the moment, you can take it as just a very popular, very common boundary map in, complex construction in homological algebra. And this black box just gives you the chain complex, and you pick the 4 boundary maps from it, which give you the parity check and meta check matrices. So you do need to pick the local checks at random. So we were talking about these initial 4 binary maps. A convenient way to encode them is in terms of polynomials that have the property that monomial to a certain power is equal to identity. So you can think of this as defining your boundary maps on a toric lattice. It's interesting geometric interpretation. We can maybe in the Q&A discuss the geometric interpretation a bit more. But really, all you need to know here is that it's very convenient to write down a binary map in terms of polynomial. It's a much more compact, much more algebraically convenient representation of a particular class of binary maps. That's because this particular set of polynomials is isomorphic to the cyclic matrices. So we're saying the binary map will be a cyclic matrix. Cyclic matrix is too cumbersome to write down on paper, so we'll be writing down the cyclic matrix as a polynomial because of that isomorphism. Then you just take these 4 polynomials, f, g, h, and I, you put them in the causal complex black box, you get for free your potentially good code. Here you also can explicitly see what those boundary maps look like. So F, G, H, and I are your randomly picked cyclic matrices that happen to be conveniently representable as polynomials if you want to. And the causal complex mapping gives you this. The reason for this specific structure is that the causal complex can be represented in terms of a wedge product. Again, there is nothing fundamental to that. There's no intuition that I have about that structure. It's just a very convenient, very popular way to turn a set of maps that are independent from one another to an actual chain complex where you have the nice properties that these boundary maps chain appropriately. And then you recognize that each one of those boundary maps is related to a parity check or meta check matrix.
Unpack them.
Yes.
So when you write the D's in this way.
So let me go a couple of slides back. I want to create this chain complex. I actually don't care about the explicit rules for at the end about what these vector spaces are. I care about what are the explicit representations of these boundary maps. Some colleague in the math department told me a standard way to build a long chain complex starting with kind of arbitrary binary matrices is to use the causal complex. And now the next question was, well, how do we write down conveniently small independent binary matrices? And if you care about that, there happens to be an isomorphism between the cyclic matrices and the polynomials. But if you don't care about that, just forget about the fact that f, g, h, and I are represented as polynomials. They are cyclic matrices.
So, but sorry, is F like, are these your small code?
Yes.
F is a single check. Okay.
Yes. So f, g, h, and I are small cyclic matrices that I picked at random. I put them in this black box, and I get these boundary maps that obey the properties that you need to have in order for them to be meta-check and parity check matrices.
And at this point, you have like a small code, not scalable with it.
Well, yes, this is you pick n at the very beginning. This is not a family of codes. That's why at the beginning I said we won't be proving any asymptotic properties. We'll be just looking for good codes. The same way when we're picking a good classical code, we just got a random matrix. We didn't try to prove anything about when the random matrix gets bigger and bigger.
But so is F a 2 to the n by 2 to the n?
F would be a much smaller matrix.
So how do you get to the big? At what point are you getting from the small thing?
So the causal complex construction just kind of tells me that if I align cyclic matrices in this fashion, I will get something that can be used as a parity check matrix for X checks, a parity check matrix for Z checks. So these are block diagonal, these are block matrices, block binary matrices. I take my F, G, H, and I matrices, and if I align them like this would be the parity check matrix for one of the for the Z checks. This would be the transpose of the parity check matrix for the X checks, and this would be the meta checks.
But I think my question is just like, so F is whatever, a 4x4 matrix.
Yeah.
Right. So then, what is n? Does that like at what point?
So n, I guess,
would small codes.
Yes.
I'm not seeing how you get to bigger. Is n just
the number of qubits would be the number of columns in this matrix,
okay?
and yeah, that's it. So there is some algebraic relationship between the quotient ring of polynomials, size, and the number of qubits. Trying to just quickly run through the rest. Here's just one instance. F is a cyclic matrix, but for me it's much more convenient to write it down as a polynomial. G, H, and I are these cyclic matrices. You use these cyclic matrices. You put them inside of the construction I showed you, and you get this code. A code with about a rate of about 10% and an okay distance.
Can you explain what the distance means there? I'm used to only one number.
Distance with respect to X errors and distance with respect to Z errors. So the smaller number here will be the actual distance.
Well, then they're the same. Why didn't you just say 9?
Because they were not always the same. So my bad, sorry, this was indeed confusing. So one quick note, there was a question about is meta-checks, how do we always talk about single-shot decoding? Another convenient way to talk about single-shot decoding is to talk about confinement. So the confinement is for a given error weight, W, just look at all errors that have that error weight, and among them, search for the corresponding syndrome that has minimum weight. So we're searching for, we fix the error weight, say 1-bit errors, and we're looking at all possible 1-bit errors. We're looking at the corresponding syndromes, and we're checking the minimum weight. If that minimum weight is very small, that's bad, because then a measurement error might be confused with an actual error. That's why if you don't have high confinement, you need to do many measurements. You need to do D rounds of measurements in order to get something that is resilient to measurement errors. But if you have high confinement, like say a single qubit error leads to a syndrome with weight 8, then it's very difficult for a measurement error to lead to the same syndrome. That is another property that people were using when talking about single-shot decodability. And bragging point here is that when we sampled randomly and searched for high confinements, our codes had record-breaking confinement profiles. I'm out of time, so I won't be discussing this table. Another cute thing is that our codes, this construction, generalizes an enormous family of other good constructions. So it's just a convenient way to write down a code, no matter, well, a code from any of these families. And we have some experimental results, but I would say, I guess the experimental results are not too interesting. It's more about the construction. So as takeaways, we have a compact representation for error-correcting codes. That compact representation is a natural, it's a convenient representation. And in that representation, it was very easy to search for codes with very high confinement, with record-breaking confinement properties, with record-breaking single-shot figures of merit. All of this is available on GitHub in the tooling we're providing. We're making a Python wrapper so that you can easily use it with Steam and the LDPC library. An early version of this manuscript is on archive. We probably will update it with significant extra tables of codes this weekend. And as a reminder, we're running a summer school. So I don't know, if you don't care about this, but like programming, please send your students to the summer school. So helping with advertisement would be much appreciated. We also, we're trying to help the open source community grow. So we do a lot of small bounties and onboarding exercises for contributing to open source. So as long as you send us a student and that student doesn't immediately start spamming us with LLM generated nonsense, that student will have access to plenty of small bounties. And yeah, we're hiring. That's all I have.
We have time for a question while Zach gets ready.
Can you say something about the geometric interpretation of those polynomials?
Yeah, so, oops. So if you have, we have this division by, x to the power of L minus 1 and so on. We have this notation in our ideal. In that notation, we are just saying that x to the, for our polynomials, x to the power wrapped around. So if we have a polynomial, we can think of a lattice, and the polynomial 1 plus x to the power of 2 means that the parity check would be between this guy and 1 hop to the x direction, 2 hops to the x direction, this guy. And if L is equal to 4, we wrap around like this. So the quotient, the polynomial quotient ring we're using imposes this multidimensional torus, and the terms in the polynomial, the powers just tell us how many jumps do we need to do in a given direction to have a parity check.
So we're using a four-dimensional torus.
Yeah, and you do just want to stress, while we use the torus to define the parity check matrix, the parity check matrix doesn't need to be local. So it's not like it's a topological code, but you can express a topological code in this notation with just a trivial polynomial.
Thanks, Stefan, again, please.
Also, it's plugged in at mirroring, but it's not showing up. Hello? Oh. Okay, great. Yeah.
So next we have Zack Weinstein from Caltech. Thanks, Zach.
Hi, yeah, thanks. Thanks very much for the organizers for putting on this workshop. It's really a pleasure to have the opportunity to speak. I'm Zack. I'm a postdoc at Caltech. Today I'm going to be talking about a project I've been working on with Sam Garrett, who's also here for quite a while. The work's based on two papers. One is on arXiv already for a couple months. The other will hopefully be on arXiv soon. Okay, so I probably don't need to tell this audience why quantum error correction is very important. Probably the most obvious reason is that quantum error correction is an absolutely necessary step for performing large-scale fault-tolerant quantum computation. So in the last 5-10 years, there's been a lot of really remarkable experiments on quantum computers on roughly 100 or so qubits that have mostly gotten away without performing real error correction. But there's certainly no doubt that if we want to scale towards order 1 million qubits and do really useful quantum computation, quantum error correction will be absolutely necessary. So this is not what this talk is about. In this talk, I'm going to be talking about quantum error correction as a conceptual framework for thinking about various aspects of quantum matter. So this is also, of course, not a new idea. You know, since the early days of topological order, it's been appreciated that there's very close relations between the very definition of phases of matter and quantum error correction. So this equation here, you can alternatively read as the criterion for local indistinguishability, essentially the definition of topological order, or as the nil-Flam conditions for quantum error correction. There are also all sorts of other interesting connections, especially in recent years. One that I like quite a bit is thinking about quantum thermalization from the perspective of quantum error correction, how it is that you obtain effectively irreversible quantum dynamics from purely unitary evolution. Another interesting topic is in high energy. This is a picture of the HAPPY code. It's a quantum error correcting code, which is a toy model for certain peculiar features of the ADS-CFT correspondence. And there are many other applications. I'm mostly going to be focusing on the first one, but it's important to keep in mind that this is a fairly useful, broad conceptual framework. So these two different perspectives are really tied together very nicely in the Toric code. I'm hoping that most of the audience is very familiar with the Toric code. Here are my conventions. My vertex operators are product of X. My plaquette operators are product of Z. So the Toric code means different things for different people. For quantum computing scientists, this is a stabilizer code with geometrically local few-body stabilizers and a large code distance, a distance that scales with the linear size of the system. And that naturally gives you a large threshold to local errors. So these properties are very attractive for people trying to build quantum computers, especially on, for example, superconducting qubit platforms where you don't have the ability to apply non-local gates. So this geometric locality is quite useful. But for condensed matter physicists, the Toric code means more than this. In fact, it means much more. For us, the Toric code is the simplest incarnation of the simplest topologically ordered phase of matter, namely Z2 topological order. And part of the promise when I say that is that if I throw these stabilizers into a Hamiltonian and I modify the Hamiltonian a little bit with essentially arbitrary perturbations, as long as these perturbations are sufficiently weak and sufficiently local, I'm guaranteed that the structure of the ground states of this modified Hamiltonian will have many qualitatively similar features to the ground states of the unperturbed Hamiltonian. In particular, the ground states will be topologically ordered, they'll be locally indistinguishable, and I could use these states to encode 2 qubits of quantum information. So based on that observation, I think many of us would believe that the protection of quantum information is not just a feature of the stabilizer Toric code, but is really an intrinsic property of topologically ordered phases of matter. However, quantum error correction is really only understood in detail for fixed points of the phase, for example, stabilizer codes. So there's many good reasons for this. An obvious one is that it's quite difficult to exactly compute information theoretic properties away from these sort of solvable limits. So here's a small list of papers that have discussed error protection in some non-stabilizer models. There's another good reason, which is that typically if I'm away from this nice stabilizer code limit, even if I have some belief that information is protected for sufficiently small decoherence, it's in practice completely impossible to design a reasonable way to actually perform error correction. And so in that sense, that makes sort of the distinction between having protected but inaccessible information and not having information at all a little bit academic. So it naturally raises two questions. The first question is, how does the intrinsic protection of quantum information break down when a topological phase is tuned away from its fixed point? And it's particularly interesting to tune towards a quantum critical point, towards a trivial phase, where you might expect the protection of information to become somewhat weak. And then the second question is, in these non-stabilizer codes, is it ever possible to efficiently decode, by which I really mean carry out the process of quantum error correction? So those are the two questions I'm going to be addressing today. So to keep things more or less simple, let me focus on the simplest deformation of the Toric code. So this is a Toric code in a transverse field. So the effect of this transverse field is to cause quantum fluctuations in the M anyons. So with this non-zero field, the ground states will no longer have zero M anyons. They'll have some coherent superpositions of M anyons around. So this model is, of course, extremely well studied. So for sufficiently small h, the topological order is stable. You can encode 2 qubits in the ground state manifold of this Hamiltonian. And for sufficiently large h, effectively the quantum fluctuations in the M anyons become too strong and the M anyons condense. And that results in a unique gap ground state which cannot encode quantum information. So let me take 2 qubits encoded in the ground state manifold of this Hamiltonian and subject it to bit flip decoherence on each qubit. So on each qubit in my system, with probability 1 minus p, I'll do nothing, and with probability p, I'll apply a poly x. So of course, in the stabilizer limit, so yeah, I should say that the effect of this channel is to incoherently create M anyons. So the transfer field is coherently creating and hopping M anyons. This decoherence channel is incoherently proliferating M anyons. So in the limit where I have no transverse field and I recover the stabilizer Toric code, this problem is also extremely well studied. So for sufficiently small decoherence strength, information is protected from this local decoherence. At very large decoherence strengths, the M anyons are proliferated everywhere. I cannot recover any encoded information. And quite interestingly, there's also a continuous phase transition separating these two limits. So the natural question is, what happens out here when I have both this transverse field and bit flip decoherence? So let me summarize the key results just to make sure the results are stated clearly. So first of all, this is a phase diagram in terms of the transverse field and the bit flip decoherence strength. You could read this curve, if you like, as a plot of the intrinsic threshold as a function of the transverse field strength. Now, it's perhaps not so surprising that deep within the topological phase, there's still some finite value of this intrinsic threshold. It requires some finite strength of decoherence to destroy your encoded information. What's perhaps surprising is that as you approach the quantum critical point, as h approaches hc, the intrinsic threshold to local bit flip decoherence remains finite. So even when M anyons are on the verge of condensing, you have really strong quantum fluctuations in the M anyons. It still requires a finite strength of decoherence to destroy your encoded information. So that's the first result. The second result is that it turns out, I should emphasize, this first result holds, I phrased it for a fairly specific Hamiltonian and a fairly specific decoherence problem, but in fact it holds for generic Hamiltonians and polydecoherence throughout the Z2 topologically ordered phase. The second key result is that for this particular model, this Toric code in a transverse field under local polydecoherence, in fact, you can efficiently decode. And it turns out the decoding algorithm is the simplest thing you could possibly imagine. It's to measure the stabilizers of the unperturbed model. And if you're familiar with problems on Toric code under coherent errors, this might a priori seem like a very bad idea to measure the stabilizers. It turns out for this particular Hamiltonian, measuring the stabilizers works quite well, and it holds for a fairly specific, due to a fairly specific property of this Hamiltonian. Namely, the Hamiltonian is stochastic, and I'll explain how that helps as best as I can. So these are the key results. Are there any questions before I explain how they came about? Yeah.
Yeah, I was just wondering if you could give it a little bit more detail about where you're going. Because from this, it seems like a relatively conventional discussion of quantum error correction ideas. I'm curious about how the decoding and encoding ideas are going to be specifically related to some of the thermalization and other physics that you're talking about.
Well, I'm not talking about thermalization at all. I'm still talking about ground state problems.
Okay.
So I'm talking about the ground state of this Hamiltonian. The difference is that this is not a stabilizer model. In particular, the Hamiltonian is non-commuting, right? That's the key point.
Oh,
so
sorry, I missed that. Thank you.
Yeah.
Okay. Yeah.
Thanks for the question.
Yeah.
Yes.
It seems not obvious why HC does not decrease as you increase the PC.
Why HC does not decrease as you increase PC. Yeah, it's a great question. I can answer that from a couple different reasons. So we're talking about, if you like, what I'm doing is I have, let's see, how to best answer this. Maybe it'll be clear near the end. Yeah, yes.
But maybe related to this, I guess you don't have a way to tune horizontally. Is that right?
I don't have a way to tune horizontally.
If you have a fixed error rate, what does it mean by move horizontally on phase diagram?
Yeah, exactly. What I would like to imagine is I start from some particular value of the transverse field. That defines my quantum code. Given that quantum code, I apply some bit flip decoherence, and I ask whether the information is protected or not. So maybe the point that you're wondering is why this phase boundary between encoding and no encoding is completely vertical. Yeah, so that will come out later. Yes?
M condensed and proliferated.
Yeah, so what I have in mind is by M condensed, I have a coherent condensate. So I have a pure state, and I have a coherent superposition of many different configurations of M anyons. That's physically very different from having an incoherent proliferation where I apply some polychannel and have a mixed state containing many different classical configurations of M anyons. Okay, so it remains I'll try to do my best to explain these results. So first of all, I have to explain what I mean by intrinsic error thresholds in the first place. So to define what I mean by an intrinsic error threshold, independent of any particular decoder, I have to define this quantity called the coherent information. So it's defined as follows. I take my 2 qubits encoded in the ground state manifold of my Toric code, and I maximally, rather than fixing one particular code state, what I do is I'll maximally entangle my code space with a 2-qubit reference system R. So here Q is my Toric code system. It's prepared in the ground state manifold, and this ground state manifold is maximally entangled with 2 auxiliary qubits, giving the state psi QR. I then take these system qubits, Q, and I decohere them to get some mixed state rho QR. And I compute the coherent information as follows. It's just this difference of 2 von Neumann entropies, S of rho Q minus S of rho QR. So the statement is that quantum information is in principle recoverable, namely there exists some recovery channel, which may be very complicated, as long as this coherent information is near its maximal value of 2. So to give you some idea of what this quantity, how this quantity behaves, in the stabilizer Toric code, it looks like this. At small system sizes, it might sort of slowly vary from its maximal value of 2 to 0. As you increase towards larger and larger system sizes, you obtain a fairly sharp transition where you are sort of stuck to your maximal value of 2 at small decoherence strengths. In particular, your coherent information gets better and better with increasing system size. And above threshold, your coherent information gets worse and worse with increasing system size. So in the stabilizer Toric code, you can characterize this coherent information pretty directly because you can essentially diagonalize the density matrix. In this problem with a transverse field where I have fairly complicated ground state wave functions, I can't analyze the coherent information so directly, so instead I'm going to rely on the replica trick. In particular, I'm going to write this coherent information as the n goes to 1 limit of a Rainey coherent information, which is related to this ratio of purities. So my goal is going to be to characterize the behavior of this ratio of purities as a function of the transverse field and the decoherence strength. The second piece of background that I need to give is the quantum classical mapping. So again, the states that we're describing as our code states are these fairly non-trivial states with large quantum fluctuations. I cannot describe them as simply as stabilizer states. Instead, what I'll use as my technical workhorse is the quantum classical mapping. Essentially, what I'm doing here is I'm going to be working in the path integral formalism. So I have a 2-dimensional quantum state, psi, and I'm going to represent it using a 3-dimensional classical statistical physics model. And the basic idea is very simple. I have this imaginary time evolution operator e to the minus beta h. I'm going to split it into a bunch of chunks. I'm going to insert resolutions of the identity, and out comes some classical statistical physics model. And I'm not going to explain this model in a lot of detail, but I'll give you some intuition for it. The model is called a Z2 lattice gauge theory. And the basic physical way of thinking about it is simply that you're tracking the space-time histories of M anyons in imaginary time. So M anyons are particles that can hop and move around due to the transverse field. They're conserved mod 2. And so in space-time, they'll form these closed loops. In particular, in the topological phase, these closed loops will be small typically. So you'll see class typical configurations will be constructed from these small closed loops. As I tune towards the trivial phase, these loops will lose their line tension and go all over the place. And you'll have big macroscopic closed loops. And in particular, you'll have non-trivial amplitudes, non-zero amplitudes for processes where an M anyon goes all the way across the system. And when M anyons go all the way around the system, they implement a logical X operator. And so when these have non-zero amplitude, you can no longer encode any information. You get a trivial phase. And the transition between these two limits turns out to be described by this 3D Ising universality class as a technical point. Okay, so let me come to the problem of interest. So suppose that I have some particular code state, psi h, and I apply bit flip decoherence on it. So I obtain this decohered state rho h. Let me try to characterize the nth purity, trace rho h to the n. It's a simple exercise to rewrite this quantity as an expectation value in an n-fold replicated Hilbert space. So here you see that I have n copies of the state psi, and I'm taking the expectation value of an operator E hat, which has this form. Looks a little bit complicated, but the physical intuition is very simple. This operator E to the gamma XX is going to, in this space-time picture, reduce the energy for pairs of world lines, of M anyon world lines, to travel together across adjacent replicas. And it only reduces this energy cost within a single slice of imaginary time. So what you should imagine here, I have this 3D space-time. Each of these colors of loops represents a different replica. So in the bulk away from this 2D surface, these replicas are essentially independent. Within this single 2D surface, I have a reduced energy cost for correlated motion of world lines across different replicas. And when I reduce this energy sufficiently, I'm going to proliferate pairs of world lines, and they'll go all the way around the system. And when these world lines can go around the system, that will destroy my encoded information. So the basic idea is that for p sufficiently small, all my anyons will be gapped. Once I crank p past a critical value, I'm going to proliferate these pairs of world lines and condense pairs of M anyons as a result. And that will destroy my encoded information. So you can relate this picture to the Rainy coherent information. As before, I apologize, this should be the Rainy coherent information on the left. I won't explain this formula in detail, but the basic point is that the Rainy coherent information is related to the free energy cost of these non-contractible loops. So the idea here is that if I'm in the phase where all my loops are short, so only one, you'll essentially, excuse me, as long as these loops are short, the coherent information will be glued to its maximal value of 2. When you start to have non-zero amplitude for these large pairs of world lines within the surface, this quantity will go to 0 up to exponentially small corrections. And then above this critical field strength, of course, you have no encoding. So the basic point here is that the coherent information is closely tied to whether these world lines proliferate through the surface or not. Okay, so now I'll come to explaining why this phase boundary is completely vertical. So this slide may be slightly technical, in which case I apologize. So in the vicinity of the quantum critical point, I can describe this classical statistical physics model as a field theory. In particular, each of my n replicas of the system will be described by a 3D Ising conformal field theory. And the effect of decoherence is to couple these n replicas by their energy densities only along a single slice of imaginary time. So that's the physical picture. And from this picture, you can compute the renormalization group equations in the vicinity of the critical points at 0 decoherence strength. The crucial observations are twofold. The first observation is that the transverse field strength cannot be renormalized by the decoherence strength. And the basic reason for this is that the decoherence is a surface perturbation. It only acts along a codimension 1 manifold. And so the decoherence cannot renormalize the value of h. The second point is that the decoherence is perturbatively irrelevant at the critical point. And this is a statement independent of the replica number, so it works also in the replica limit. So the first observation tells you that if you park yourself at h equals hc, the RG flow can only go either straight up or straight down. And the fact that it's perturbatively irrelevant tells you that it has to go straight down. So that's how you arrive at this conclusion that you must have a finite value of this threshold even as you approach the critical point. So that's the basic idea. Any questions about that? Yes.
Yeah, what do you mean? Like, more particularly, what does it mean to have imaginary time coupling? And I'm kind of totally lost about this description. Could you give something for a dumb computer scientist?
Can I give something? Can you be more specific?
Okay.
What would you like?
I guess what I'm failing to understand is I'm just not understanding the argument you're trying to make or the objects you're reasoning with. And I was hoping you can give me some intuition about how this is going into discussing like anything.
You went out for 10 minutes, so you could have been here. Maybe you heard, no? You went out for about 10 minutes.
Oh, that long? I'm sorry.
But go ahead.
I mean, maybe we could interpret the question as like, for people who are not familiar with
Yeah.
your path integrals, can you give like a brief?
Oh, there's path integrals here.
about that?
Yes. So the basic summary is that my quantum states, which have non-trivial quantum fluctuations due to this transverse field, can be described in a path integral formalism as a three-dimensional classical statistical physics model. The effect of decoherence you should think about as some codimension 1 defect within this path integral. So it's acting only within a subdimensional manifold of my three-dimensional system. I see you're not happy with this already.
So the imaginary time, is that just trying to model dissipation? Is that
No, the imaginary time is modeling the quantum states, the quantum states itself. I'm describing pure quantum state using this imaginary time. So I can go back several slides.
Because this is kind of, maybe we should move on.
Yeah,
because
that's
that's
fine.
our-
You guys can
Sorry.
talk about yeah, I'd be happy to talk more often.
Yeah,
I
afterwards.
think it was, yeah.
Okay. Yeah, so I apologize, this is somewhat technical. Okay, let me nevertheless give some comments. So I discussed a statistical physics mapping and a field theoretic argument for a specific model under a specific decoherence channel, but the argument holds for more general Hamiltonians and for arbitrary local polynoids. And in fact, you expect a finite threshold throughout the phase diagram. You can look at phase flip errors in particular. It turns out this particular case is exactly solvable. And the threshold for phase flip errors is completely constant, independent of the transverse field strength. However, this argument necessarily doesn't say anything about the size of the threshold, which is a non-universal quantity. And of course, I'm using the replica trick in this argument, which is not a rigorous tool. It can't always be trusted. And of course, you could ask, as I said in the beginning, is it possible to decode? And it turns out in this case, the answer is yes. So suppose that my decoherence strength is below this intrinsic threshold. You can ask, is it ever possible to recover the encoded quantum information? So if I were in the stabilizer case, so I'm just working at stabilizer Toric code under bitflip decoherence, the thing you would do is you would just measure the stabilizers. And so what you would do is you measure the stabilizers and you see some syndrome, and then you try to pair the anions up in some way. For general states within the topologically ordered phase, this is actually a very bad strategy. And the reason is because you have coherent fluctuations of your anions within general states, and this measurement of your stabilizers can collapse or reveal encoded quantum information. For this particular model, this Toric code in a transverse field, measuring the stabilizers actually it turns out to lead to an efficient decoder with a fairly large decoding threshold. So in fact, the information within this phase is also efficiently recoverable. We have a conjecture which we haven't been able to completely rigorously prove, although we have strong analytical arguments, that this decoder is actually optimal in the sense that the decoding threshold, the threshold I get for this particular decoder where I measure the stabilizers, agrees with the intrinsic threshold defined by the coherent information. And the key property of this Hamiltonian that guarantees that this is possible is that the Hamiltonian is stochastic. So this is a somewhat technical point. The definition of a stochastic Hamiltonian is that its off-diagonal matrix elements are non-positive. What it really means in practice is that you can describe these quantum states using the quantum classical mapping. So I'll try my best to explain how this works, at least at an intuitive level. So the intuition for why measuring stabilizers is actually a good idea, again, comes from the quantum classical mapping. So once more, if I have one of these ground states of my toric code in a transverse field, I can describe it to excellent approximation using imaginary time evolution. So what I'm doing here is I'm taking some particular reference state psi naught. I'm evolving with imaginary time beta. Beta I want to take to be large so that this effectively projects me into the ground state manifold. And once again, I can think about this in terms of the quantum classical mapping as being described by world lines of M anyons in spacetime. So if you consider some fixed values of these M anyons after doing a measurement, you should think about these M anyons as arising from one of many different trajectories in spacetime of their world lines. So the observation here is that these world lines, given the configuration of M anyons, can be sorted into homology classes. So these two world lines on the left are homologous. You can get between one and the other by adding contractible closed loops, whereas this class of world lines is non-homologous to the first two. So these two differ by non-contractible loops. And what that means is that these two space-time processes differ by logical operators. So the key observation here, it turns out that for typical syndrome measurements, only one of these homology classes contributes any non-negligible amplitude. And in particular, when this different homology class contributes a negligibly small amplitude. So a theorem we can prove with fairly mild physical assumptions is that if you take one of these pure stabilizer states and you measure a syndrome, you measure the stabilizers, in fact, this measurement acts unitarily on these ground states. So that means even though your state has some non-trivial quantum fluctuations, when I perform the stabilizer measurement effectively just rotates unitarily my code states up to exponentially small corrections for all typical syndrome measurements. So this is for measurements of the pure code states. I don't have decoherence at this stage, but this is an important sanity check for suggesting that measurements can be useful as a decoder in the first place. So I wrote this as a theorem, but of course you can check this numerically very efficiently. It turns out you can construct an efficient Monte Carlo implementation of this optimal decoder using the worm algorithm. So just to say it in more detail, I measure the syndrome. I see some configuration of M anyons. My optimal decoder is to compute the wave function amplitude of each homology class of world lines. So there's 4 different homology classes of world lines. I want to compute the amplitude of each of them, and I want to construct a pairing of these anyons that pairs the anyons up such that I get these contractible closed loops in spacetime. So here's a plot of the recovery fidelity, again in this pure state setting, as a function of G, roughly the transverse field strength. And what you can see is that everywhere within the topological phase, you have extremely high fidelity of recovery. And then once I leave the topological phase, that starts to decay. And you get this nice scaling collapse. So the punchline here is that throughout the whole topological phase, if I just measure the stabilizers in these pure code states, I can recover the encoded state with high fidelity. So stabilizer measurements of these pure code states preserve the quantum information with high fidelity. Finally, I can come back to the case of polydecoherence. So to remind you of the setup, I have some toric code state, transverse field toric code state, which I subject to polydecoherence. And then in my attempt to decode, I'm going to measure all the stabilizers. And I obtain this state rho h of s with some probability ps. Now you should think about this resulting state as arising from some combination of bit flip errors acting on bit flip errors E and some world lines of M anyons in the states. And when I measure the syndrome, I only see the combination of the two, the mod 2 superposition of the anions from the bulk world lines and these errors, which you could think about as living on the surface. So the basic point here is that it turns out, because this Hamiltonian is stochastic, once you measure the stabilizers, it will convert these coherent anion fluctuations into an effective incoherent error channel. And I can decode just by treating these this problem as if it's a problem of two different incoherent errors. Question?
Just clarify, because I thought you said in the previous slide that these measurements act like unitary rotations on the code space. So how, but now you're saying stabilizer measurements are acting like an.
Oh, sorry, yes,
Yeah,
in the presence of additional bit flip decoherence. The point is that once I measure the stabilizers, I'll have an incoherent mixture of different logical sectors. I won't have any coherences.
Oh.
Yeah, thanks for the question. Right, so in the end, I can decode just by thinking about this as if I have two different incoherent error channels, one associated to the actual bit flip errors, and the other associated to the world lines in the bulk. So I have some conditional probability distribution of these world lines and errors conditioned on the syndrome. I can split these different world line and error configurations up into 4 homology classes, and the optimal decoder, assuming that I've measured the stabilizers, is to compute the probabilities of these 4 homology classes and decode in the most likely one. So here's some numerical results, again, using this worm algorithm for an efficient implementation of the optimal decoder. So on the left, I have, so G is not quite the transverse field, but you could think about it morally as a transverse field. So I'm 0.976 away from the critical point at GC. So you can see, if you're familiar with the stabilizer Toric code, where the threshold is 0.109, my threshold has reduced reasonably from the value at the stabilizer limit, but not that much. Here I'm 1 in 1,000 away from the quantum critical point. So I really have a correlation length that's appreciable compared to my linear size of the system. You can see these curves are starting to collapse in on each other. They're starting to overlap, but nevertheless, there's a very clear crossing at some reduced value of the threshold, which is now 0.09-ish, a little bit above 0.09-ish. So reduced from the stabilizer limit, but not that much. And here's a plot at fixed polydecoherence strength, just tuning across the quantum phase transition. And you can see once again that you have a nice crossing. And so everywhere within the topological phase, at this value of the decoherence strength, you can measure and correct the decoherence. So the basic punchline is that the decoding threshold as G approaches GC is only reduced slightly from the value in the stabilizer Toric code. So here's my summary. So again, I was studying this transverse field Toric code under bit flip decoherence. The first result is that quantum information is robustly protected from local polydecoherence throughout the topologically ordered phase, even as a quantum critical point is approached. And the second result is that in the transverse field Toric code under bit flip decoherence, so this specific model, information can be efficiently recovered using stabilizer measurements and Monte Carlo decoding. So I have some additional results just to mention for experts. So you can consider what happens when you add additionally a longitudinal field to your Hamiltonian. Phase flip decoherence I mentioned very briefly. There's interesting connections to strong degree spontaneous symmetry breaking. There are other similarly related quantum error correction problems in these non-stabilizer codes to discuss, like quantum error correction in the ferromagnetic transverse field Ising model. So with that, thank you for the attention, and I'm happy to answer more questions.
Questions for Zack?
Yeah, Yuma.
So in the transition, when you find an P and tune your G, which is essentially H, do you find the Ising's 3D Ising universality?
Yeah, so I should have put some critical exponents. Yeah, this is a scaling collapse with no fitting parameters. I've just put GC from the known critical point, and I've picked nu, the correlation link exponent from 3D Ising.
It's the same U and all.
Yes. Or sorry, no, excuse me. Oh, I'm very sorry. I should have had better notation. These nus are different. These nus are the nus from 2D Nishimori random on Ising. So these transitions are consistent with Nishimori random on Ising. Yeah.
The various no-go theorems about good rates and good distances were typical
topological codes, well, typical for me is, do you expect that they are still here, or is there a chance that this would have excitingly good distances or something like that?
I don't see any reason why. I think that these codes would be strictly worse than the stabilizer limit, is my guess. I don't think these are useful as a practical error correcting code. I think these are primarily interesting as a lens into understanding these phases of matter.
Let's stay for the coffee break while we keep on time. Thank Zack again. Well, not yet coffee break. Not yet. It's your one more. Ehud Altman, are you? Yeah, it is coffee break.
Sorry, I literally didn't hear.
Yeah. Okay. Start now. Okay, so
He's a second year.
what I'll talk to you about today has some tangential relation to, or maybe pretty close connection to quantum error correction, but I'll frame it in a slightly different way, maybe similar to what Zack did. My concern would be mainly like how we understand error correction can give us more insights toward phases of matter. And another perspective would be image reconstruction, as you would see. And image reconstruction or is something that people are doing now a lot with AI, like, for example, denoisers in diffusion models, where you basically train them on reconstructing images, and then they can generate new images. I'll show in what way this is related to quantum error correction, and in what ways it's different. This work was done with amazing students and graduate students and postdocs in Berkeley, specifically Vlad Temkin and Pablo, who's a postdoc, also in collaboration with Senke in Santa Barbara, and Daniel Podolsky, who is a visitor in Berkeley. Okay, so let's start with image reconstruction. So suppose I give you a blank image, and then another image with just two binary pixels turned from plus to minus. So let's say our picture is, our TV screen is super simple. It just has binary pixels either on or off. So this is a picture, and easily you can distinguish them. Now let's say you had some binary noise, and the binary noise keeps parity. So it creates only minus pixels, dark pixels in pairs. And then you get this noisy picture from here, and you get another noisy picture from here. And this is how it looks. For example, this pair shut off this other pixel. you can imagine that at some point, it'll be hard to distinguish what was the original image. And there is a big question of how to reconstruct this. It turns out that this question is equivalent to the problem of strong to weak symmetry breaking and spontaneous symmetry breaking of Z2 symmetry. And it's also equivalent through a duality to decoding of Toric code with Z noise. And it maps exactly to a classical inference problem that can be written in terms of a statistical mechanics model. That turns out to be, in this case, the random bond Ising model. So this problem of reconstructing an image, which you can see intuitively why it's related, if you know about how decoding of the Toric code is done, why it's really directly related. You can think of these minus signs as syndromes, and you need to match them in order to reconstruct the original image. And it turns out that this inference problem is indeed a StatMech model. What I'll talk about here is what becomes different when you want to distinguish, instead of classical images, you want to distinguish quantum images. And a quantum image is, an example of a quantum image is, here I have a vacuum, and on top of this vacuum, I create a bell pair, say, with very distant spin halves. And I want to distinguish these two images when I start to turn on some SU2 symmetric noise. That's an example of where the SU2 symmetric noise creates, again, small singlet bell pairs of spin halves. And at some point, it makes it harder and harder to distinguish these two pictures. This I cannot really frame completely as a classical problem because I cannot even draw it, right? I need to kind of symbolically draw that it's a singlet, but it's not really an image. It's an entangled state. So the question is, what is the difference between distinguishability transitions in classical images and quantum images? And that will be directly related to quantum error correction in abelian versus non-abelian codes. So let me take a step back and much more slowly discuss this classical problem first. So let's talk about Z2 strong to weak spontaneous symmetry breaking and understand it as a kind of image reconstruction problem. So what we, again, as I mentioned, we start from a symmetric state. For example, this state, which has a plus pixel on every side. In quantum mechanically, we can just write it like the plus x state, plus in the x direction. And this is the, I call it the xy state because at site x and site y, I apply z operators, and that creates this pair, okay, of minus signs. And I want to distinguish between them. When I subject the system to a strongly symmetric quantum channel that creates neighboring minus pairs, negative parity pairs. So this is the channel. And this is what it does to your initial states. And when I say strongly symmetric channel, what I mean is that the Krauss operators commute with the symmetry, with the Z2 symmetry. And this means that it preserves the strong symmetry of the density matrix. Originally, it was clear that it had a symmetry to only one-sided application of the group elements, and it's preserved by this channel, the strong symmetry. So if it's preserved by this channel, you can imagine maybe this can be spontaneously broken, the symmetry, in some way. But I mean, spontaneously broken symmetry in spontaneously broken strong symmetry is not a conventional kind of phase transition, because if we tune the channel up, well, there is nothing really in the correlations between, let's say, order parameter of usual Ising order parameter Z2, Zx, Zy, always has exponentially decaying correlations, and there is no singularity and no phase transition in these normal physical observables. So what am I talking about, strong to weak symmetry breaking transition? So it turns out that there is a transition in more subtle information theoretic quantities that are not linear in the density matrix, and therefore are not usual observables. And we'll discuss how we can observe these transitions, really. To see that it's convenient to see that there should be a transition, it's convenient to rewrite the same channel in a vectorized form, where the density matrix is just written as a vector in a doubled Hilbert space. And then the Z and Z bar correspond to Z acting from the left on the ket, and and Z bar is the Z acting on the bra. In this form, it's clear that what this channel does, it proliferates pairs of ZZ bars until eventually you could imagine that they want to condense. If you took this P to be small, this is like, and did it many times, this would be like an imaginary time evolution, where the imaginary time evolution projects you onto a state where this ZZ bar is condensed. So what does it really mean for this ZZ bar to condense? And this was pointed out in this paper, that really the correct information theoretic signature of this condensation is the fidelity between the two states. Let's say this state and this state, where I take X and Y to be very far from each other. The fidelity, when there is zero fidelity between these two states, it means that they're perfectly distinguishable from each other. And when there is some finite fidelity, even when I take this distance to be far away, it means that these two states are not perfectly orthogonal to each other. They're not distinguishable from each other. And you can also see it, instead of the fidelity, by the KL divergence. That is just order 1 for, it's just order 1 for, maybe it's the opposite, for P less than PC, yeah, it grows linearly with the distance, which means that these states have diverging. They're divergent from each other, while they're very close to each other when P is more than PC, and they can be distinguished. So this is really the operational meaning of this phase transition of strong to weak symmetry breaking. By the way, the reason why it's called strong to weak symmetry breaking is that this order parameter that condenses, as you see, it anti-commutes with this one-sided symmetry, where I act with product of X only on one side and not both sides. But it commutes with the weak symmetry that conjugates the density matrix from the two sides, right? Because then you apply product of X on both sides, and it commutes with this. So this is an order parameter. This condensing object is an order parameter of the strong symmetry. So to summarize, strong to weak spontaneous symmetry breaking is a state. So in this strong to weak symmetry breaking, the state with a pair of distance Z2 charges becomes indistinguishable from the corrupted vacuum. Okay, so if you want, the strongly symmetric state is a state where if I create a charged excitation, -1, it's a perfectly orthogonal state to the ground state, to the vacuum. In the strongly symmetric spontaneous symmetry breaking state, that excitation becomes like part of the vacuum, if you want. Yeah.
Could you clarify what you mean by corrupted vacuum?
Oh, yeah. Corrupted vacuum is this, like the vacuum on top of which you apply the channel. And the corrupted vacuum becomes indistinguishable from the corrupted image state.
And when you apply the channel only once, or you apply it?
Here I apply it just once. Yeah, I applied the channel once, and the tuning parameter is P. You could use continuous time and apply Lindbladian, and then there would be a finite time transition. So here I just do it discretely, right? And the tuning parameter is P. Again, the operational meaning, what is the operational meaning of this strong to weak symmetry breaking? I want to argue that the operational meaning is whether you can decode it with an optimal decoder. And what's the optimal decoder here? When I measure in the local X basis, these are the measurement outcomes, it can be plus or minus 1. Actually, the density matrix is diagonal in this basis. So finding the fidelity, the quantum fidelity between the two density matrices is exactly the same as finding the classical fidelity between the probability distribution in the X basis, in the charge basis. So really the problem of this fidelity becomes a completely classical problem, and it's not really surprising because, yeah, you see it as images. So it is really a classical stochastic problem. In fact, in this abelian strong to weak symmetry breaking, in particular Z2, there is no need for quantum mechanics to define strong to weak spontaneous symmetry breaking, although it looks weird that, if the strong symmetry is a one-sided symmetry of the density matrix and all this, but in reality, the operational meaning is the same as some transition in a classical stochastic model. And then the optimal recovery becomes a Bayesian inference problem that basically I can write like this. I need to sum over all the possible error chains, and given the error chain, the syndrome configuration that results in this error chain. And this turns out to be exactly the random bond Ising model. I won't go over this, but this is known from Kitaev decoding of the Toric code. And the Kell divergence between the two density matrices becomes just the free energy difference between two configurations and this, the average free energy difference in the Ising model. And to recover, we apply, basically, in order to recover, we reapply the error from the class belonging to the larger of the two probabilities, PXY or PA, and then we recover the original image. And you can go beyond U1, Z2 to U1. It's another example of strong to weak symmetry breaking. In this case, the channel will create, instead of plus minus pairs, okay, it in principle can create n particles here minus n particles here, or a particle and whole in this case. So, and you want to distinguish this, and the channel, sorry, these are the two images you want to distinguish, and the channel is this. It can be written in terms of quantum rotors, which create particle hole at nearest neighbor sites and mess up this picture a bit. And you want to distinguish them. But again, just like before, the density matrix is diagonal in the charge basis. So the recovery becomes Bayesian, classical Bayesian inference problem that in this case can be just very similar to the case of the Ising model, which is basically a loop model anchored on the syndromes. In this case, it's also a loop model anchored on the syndromes because the partition function needs to sum over all the possible error strings that could have happened that are consistent with these syndromes. The only difference is that in this case, it's directed loops. And the reason it's directed loops is because now if we have syndromes, they also have, a number and not just plus or not just minus. So they're not just there, they also have a sign. So we know the direction from the plus to the minus, right? So the loops, so that becomes a directed loop model, and that directed loop model is equivalent to an XY model with a strange kind of stretch of disorder. And what provides the quench disorder again is this syndrome configuration that we see in the experiment. So we can use this kind of StatMech model to decode, and at the optimal decoder happens to be on the Nishimori line. It's not happens to be, it's something pretty fundamental on the Nishimori line of this random bond, well, it's a random XY transition, turns out to be a KT-like transition. This was studied also together with Vlad and together with Zack here in this paper. There are very interesting aspects of this phase diagram, but you can ask me or Zack about this after. It's not the main topic of my talk. So far, it's still abelian, and it's a completely classical problem. That's my main point. So summary for abelian phases. The density matrix is diagonal in the symmetric basis. It becomes essentially a classical stochastic model because the quantum fidelity is the same as the classical fidelity. And my my optimal decoder is a Bayesian inference problem that I can phrase as a local StatMech model. It's basically the same as some kind of image reconstruction problem. So now my main point is, what do we do about the quantum images? And our model to test this would be SU2 symmetric model. So here is the definition. Yeah, okay, so I'll define the model more carefully, but roughly speaking, it's going to be a model where the channel is going to be SU2 symmetric, so it will create pairs, singlet pairs on nearest neighbor bonds, and we want to distinguish between two entangled states, like this, or one that's not entangled, just a vacuum, and some singlet state, which is entangled with singlet being par separated. Okay, so this will be the problem, but we'll have some essential obstacles. So one obstacle that turns out to be not essential, but we have to pass it, is that if you think about it a bit naively, there is a possibility of non-commutation between errors on adjacent links. Because if we have ZZ errors or these U1 errors, they're always commuted. But if you think about spin variables, they don't commute. So if we have if we want to construct a SU2 symmetric Krauss operator, it would look like something like this, S dot S, or it will involve S dot S, and they will not commute between different adjacent bonds. So that could be a problem. It's ambiguous how you apply the channel, what you apply first. Another problem is that quantum channel inserting bell pair creates an entangled density matrix. So it doesn't have a description in terms of a stochastic model. You can't really write it as a diagonal density matrix in any basis. So in any local basis. So how do you phrase the classical stochastic, the classical inference problem? How do you do decoding? Another problem that is not unrelated to this is that if we measure the local syndromes, for example, if we create spin half pairs and we ask on what is the EREP, where do we have spin half pairs on the lattice, we don't gain the full information because it doesn't tell us these spin half pairs, what do they fuse to, whether this pair will fuse to 0 or to spin 1. This is information we don't have. Another way to say it, there are internal degrees of freedom in each EREP that we don't project on. So the projectors are not rank 1 projectors. And last, which is special to SU2, what we've seen before is that in these abelian models, we map to a StatMech model. In the case of Z2, it was an Ising model, random bond Ising model. In the case of U1, it was an XY model. It was always a model that had the symmetry of the original channel. In this case, if this will come out as a model with SU2 symmetry, then we know that a StatMech model with SU2 symmetry or O3 symmetry in 2 dimensions has no transition. It's always in the disordered phase. And the question is whether the quantum image is really extremely robust and we can always decode it, or there is something wrong with, or something goes wrong with this mapping. The mapping is not to a local nonlinear sigma model. So we'll also address this problem. So let me address these. So the main point of the talk will be to address these problems, which I think they're all kind of fundamental and interesting. The first one is the least interesting. It's probably the most technical, and it's easily solved. So the first one, the way to solve it is work in a model that instead of using like a single EREP on each side, a single spin, you work with a much larger representation, such as the regular representation. Basically, it's a quantum rotor representation on each point. And essentially, this is what we did with U1, although we didn't have to, where at every site we have a group element, and the group element in U1 was parameterized by the U1 phase theta. In the case of more general groups, I can formally define a group, Hilbert space defined by group elements on each side. One can use these, define also Wigner matrices that help us to write another orthonormal EREP basis for this quantum spinning top. These are called the Peter-Weil basis for the regular representation. So we can also have an orthonormal basis in terms of representation. Note that on every side, I have not only all the possible spins, I have multiples of each spin. So for spin half, I have 2 species of spin half on every side in this representation. Okay, so this is a bigger representation that allows more freedom, and you can now design channels that commute between different adjacent bonds. By the way, the initial state is always the singlet on, I will use the initial state, the trivial initial state to be always singlet on each side, except we want to distinguish it from another state where it's singlet on every side, except a spin half pair that's separated by a long distance. Okay, so this is the representation we'll use, and now we can define this channel. This is a channel with probability pj inserts a pair of j representations on nearest neighbor links, and this is how one defines the channel. It's a little technical. It's not really important for now. There are other choices of channels we can use. This is one kind of very symmetric choice. It will turn out to be a little bit too symmetric, so, but never mind. And also, we'll make it even simpler for the numerics later, especially, that pj is going to be non-zero only for j equals half. So we're going to only create singlet pairs of spin halves, and the channel is not going to create higher ones. So either does nothing or creates a pair of spin halves. And as a technical comment, for finite groups G, not SU2, what we constructed is really dual to the ground state of the quantum double model under purely charge noise, which creates pairs of charged anions in the quantum double model. So what I'll say now is directly related to decoding in the quantum double model, in particular for SU2 level K. And but the same framework can be used for S3 and so on. We are also using it for that. Okay, so now let's get to the operational part of decoding. So the first question is what syndromes we want to measure. The first thing is, you notice, in order to detect strong to weak symmetry breaking, you need to measure syndromes that are SU2 symmetric. So the measurement channel can't break the symmetry. Otherwise, you get a completely different transition. And the simplest and most natural thing to measure that's SU2 symmetric is just a local EREP. So get a picture like that. What local EREPs were created by the channel on every site. But one has to note that the density matrix is only block diagonal in this measurement. It's not diagonal in this basis, in measurement basis. So in particular, if I look at the quantum fidelity, there is an inequality. It's going to be strictly smaller than the classical fidelity associated with this measurement channel. So for a given measurement channel, I have an inequality. And that means that, strictly speaking, what we're doing is we're finding a lower bound to the true strong to weak symmetry breaking, transition. But we can think of it as the optimal decoder given that measurement channel. We want to find the optimal decoder given that measurement channel. So most of the time now I'm going to treat, and I'm going to comment on better measurement channels maybe, but I'm going to treat this measurement, which is our easiest in practice. So meaning measure locally what are the syndromes. Okay, so doing that, now we can map it to a Bayesian inference problem. And very similarly to the case of U1. In the case of U1 symmetry, we indeed get a nonlinear sigma model with disorder corresponding to insertion of charges at the places where the syndromes are. So this was the strange disorder in the nonlinear sigma model. And in this case, it was U1 nonlinear sigma model. And just like we anticipated, we also get O3 nonlinear. Actually, we get O4 for this channel, and because it has some extra symmetries, but morally, it's the same thing. We could devise a different channel where we'd get an O3 nonlinear sigma model here, times some syndromes that basically project you on a specific branch of the density matrix. So superficially, it looks like an O4 or an O3 nonlinear sigma model with some symmetric disorder. But there is a crucial difference because by projecting to the irreps, we haven't projected the wave function completely, as I mentioned. We haven't specified what are the fusion channels between these different syndromes. And in fact, you have to, so in the abelian case, there is, once you know the syndromes, you know exactly the fusion channel between every two. You don't know that in the case of SU2 or S3. And in principle, because this is not known, in the Bayesian inference problem, you have to sum over all the possibilities. So you can write the possibilities as a tree. So at the base of the tree, you have this nonlinear sigma model. You have this disorder, which is related to the fixed syndromes in the leaves. That's what you measured. But then you have to sum over all the possible ways that these can be paired into an irrep. And then pairs of pairs have to, at the next level, be paired, and so on and so on. So you have to sum over all of these. So what you get is a nonlinear sigma model in 2D with a tree on top of fluctuating degrees of freedom that you have to integrate over in the partition function. And what that does is, so the Statnik model involves the sum of all the possible fusion outcomes at all levels of the tree. And this can potentially generate long-range interactions between degrees of freedom in the 2D lattice, and at least potentially, we don't know yet, give rise to a phase transition that you can't have in just a local O3 nonlinear sigma model. So is there really a threshold in this case? To test this, we need to do a numerical check. And remember, what we want to compute is the classical fidelity given this measurement channel, which is this. And we can rewrite it in terms of Bayes' law as a sum over error strings that we need to draw from a uniform distribution times the distribution of what are the syndromes given the error string that we draw, times this thing that can be phrased as some correlation function in this. It's like long-range correlation function. So what do we do? What we actually do, and we're going to do it numerically, is to sample the probability of the, sample the JV probabilities in this way. First, sample errors. For a given error, we sample one by one the syndromes by contracting these tensor networks. I'm nearly done. And then we evaluate the correlation function using a worm algorithm. Remember, after doing, you can think of this average, just like in the random bond-Ising model, as a disorder average. And this thing is a correlation function where you have to sum over all the possible error strings that could have been consistent with that syndrome configuration. So the sum over all the possible error strings that could have arisen is done by using a worm algorithm. Again, a worm algorithm is an error worm that has a head and a tail. The difference here is that the head and the tail have to have a bell pair between them. They have a spin half at the head, a spin half at the tail, and the worm goes around and starts to fuse between and look at all the fusion channels it can have between it and syndromes along its way. And you wait until this, and this is an open configuration until you, and legal configuration is obtained only when the head meets the tail. So every time the head meets the tail, you get back a closed configuration. But in the meantime, you can measure a correlation function which corresponds to an open configuration. So as usual in the worm algorithm. So we've done this, we've implemented this numerical test, but so far we don't yet have an answer. So I'm talking about work in progress. I have never talked about this before, which means, maybe I'm bullshitting. So try to catch me. But it's at least something I'm excited about because we don't have an answer yet. So maybe soon, whether there is a transition or not. My suspicion, I'll tell you my suspicion. My suspicion is that there is no transition. And the reason is that as long as there is no bond percolation, the error clusters are kind of separate from each other. And then the tree is mostly populated by zeros, and it just locally populated by non-zeros. So it doesn't really mediate long-range interactions. On the triangular lattice, you can get percolation transition for p less than half, in which case, beyond this percolation transition, there is a chance for mediating long-range interactions and getting O3 transition even in 2D. So that's my expectation, but maybe I'll be proven wrong. So, okay, and last thing before I finish, towards optimal decoding. So what I chose so far was just measuring local syndromes. But of course, this is not all the information. And I can measure more information by measuring groups of syndromes and asking what they fuse to. That is a legal measurement. It's a non-local measurement. It's harder to do, but it's in principle possible. And if I did that, I would if I fix pairs of syndromes and measure their fusion outcome, I basically fix the values of the next level in the tree. And if I go higher in the tree, I fix the value. To larger groups of syndromes, I fix the values even higher in the tree. And there is, using the data processing inequality, you can show that the fidelity is increasing as you go to higher and higher levels, which means that you are expecting to get larger and larger values of the critical probabilities. So we get better and better decoders by going up the tree. And when we go to the entire tree, actually, we completely freeze out all the fluctuations of the tree. And then besides some strange kind of non-local disorder, the model is essentially local. There are no fluctuating non-local degrees of freedom. And in this case, I definitely expect that there is no phase transition because it's an O3 model. But who knows? We need to check that too. So this should be checked. So to summarize, abelian strong to weak spontaneous symmetry breaking is completely equivalent to a classical Bayesian inference transition. Non-abelian strong to weak SSB is essentially a quantum problem, a quantum imagery construction problem. And one can phrase it as a Bayesian inference transition only when we decide on a set of measurements. And usually these would be not suboptimal. And then it's a legal Bayesian inference transition that we can write down as a classical StatMech model. And there is still an open question whether SU2 image reconstruction transition occurs in 2D. I told you my speculation that triangular lattice is more likely than square lattice for some obscure reason. Now, another point is that our analysis is equivalent through Cramer's one-year duality to decoding of non-abelian quantum error correcting codes with only charge noise, namely noise that creates only charge anions and no flux anions in the quantum double model, for example. And it would be very interesting to generalize this to add both flux and charge noise. So what we do now and the kinds of decoders I showed with these worm algorithm decoders can be used just as they are to decode as a quantum error correcting code as a decoder for quantum double models, but only with charge noise. And the next step is to generalize it to more generic types of noise. And the last thing, if we want to use it for quantum error correction, this is, of course, a non-local decoder. Can we have a local decoder version, maybe even if it's not optimal for this, like to have autonomous quantum error correction? So thank you.
Yeah, quick question. Can you comment about the efficiency of the decoder?
Efficiency, yeah, the decoder is efficient.
Okay.
Yeah, it's efficient. It's a warm algorithm, and it's efficient. There is one reservation that, unlike the usual warm algorithm, where it's very easy to compute the rejection probability, here, every time you want to compute the rejection probability, you need to contract the tensor network. We haven't done the full analysis whether in all cases that tensor network contraction is efficient or not. So it's possible that if there is a transition close to the transition, it becomes inefficient. That's something we need to still check.
So it's kind of still open, but your conjecture is that it's efficient.
Yeah.
Okay, great.
It seems like your noise will only ever at worst create a charge 2 excitation.
Yes.
Could you restrict yourself to those representations?
Yeah, this is what we actually do. That's the main reason, because the numerics is much simpler, that's why we restrict it to that channel. So the tensor network is really simple. It has basically virtual degrees of freedom that it's basically a PEPS with virtual degrees of freedom that are spin halves. If we go to a larger channel, the PEPS becomes higher and higher bond dimension. And in principle, if you allow all representations, it will become intractable. Yeah.
And that's the sphere that you had.
Yeah, but since the symmetry is not changing, we don't think it will actually change anything about the universality class of the transition or anything like that. But it's going to be just less tractable. So we use this regular representation, which is huge, but then we really truncate it to the lowest to spin 2.
Next speaker again.
Oh, yeah.
Yeah. The point is supposed to be complicated than not.
Next up, we have that and Stony Brook.
So thank you very much. Is the mic on? Yes. Okay. So thank you very much for the invitation. I'm having a lot of fun here in Minnesota. It's actually my first time in Minnesota. It's such a nice place and weather to be this week. So I'm going to be talking about a couple layer construction of product codes, and this is in collaboration with Shuyu and Tsuchiya. Shuyu is actually here. He's in the red jacket in the back. So I cannot answer any questions, who to go to. So my context here, I'm going to be talking about stabilizer codes, and of course that has already been introduced in this workshop. And stabilizer codes, although they are very simple, they have very deep connections to topological phases of matter, such as Toric code and Haas code, which are geometrically local codes constructed from these stabilizers. But of course, we also know that there's some restriction if we have only geometrically local codes. And in particular, if we try to construct codes with good parameters, such as this number of encoded qubits or distance, we are fairly constrained if we embed our system in, for example, a d-dimensional Euclidean lattice. So there are some certain bounds. For example, a Toric code, as an error correcting code, has very bad parameters, right? As you scale the system size up, you still only encode 2 qubits. So although this is a good topological code, the topological code, because it only depends on the topology, it doesn't encode a lot of information. Nevertheless, there is actually a wider range of codes if we relax geometric locality to something called k-locality. And that is, you don't care about the geometric locality, you only care about you only want to finite things to interact at a time. And recently there has been a great progress in coming up with these good so-called quantum LDPC codes, which we heard about this morning. So my goal here is, for example, as a condensed matter physicist, we might be wondering about how to think of them as a phase of matter. And there has been also recent work on, for example, studying these error-correcting codes as a gauge theory, also stability to perturbations. There's also a related literature related to that going beyond topological phase. There are also work closely related to this when people started thinking about fracton phases, which are beyond topological phases, but still geometrically local. And this quantum LDPC code is a natural generalization of that, where we further relax geometric locality. So that's an interesting question. But what I want to talk about today is trying to think of a very particular class of quantum LDPC codes, and those are called product codes. And this was introduced in the literature some time ago, maybe 10 or 15 years ago. And the construction is very simple. You take in, for example, two classical codes. For example, it could be the 1D repetition code or 1D Ising model. And then abstractly, you can construct a two-dimensional quantum code. For example, you take the 1D Ising model, and then there is a product which you can think of as a tensor product. You tensor them together, and you get the so-called Toric code. But what I want to try to answer today is, of course, we can think of this abstractly mathematically using, for example, the chain complex, which we heard about this morning. But what I really want to answer is how, if I have a bunch of 1D Ising models, how do I actually assemble it and form this Toric code? So if I give you these 1D Ising models, how do they fit in together rather physically in space, rather than abstractly as a mathematical construction? There has been very recently nice work by Tibor Rokovsky, Vedeka Kabani, answering partially this question. But what I want to do today is, it will be closely related to this, but it will also generalize to when your input code can be quantum codes as well. So for example, you can also do this construction when you can product two quantum codes together, not just classical, and I'll talk about that in a bit. And we have a very nice interpretation in terms of how these classical or quantum codes gets coupled together to form this product code. And the answer of this question actually has a very condensed matter feel to it. And it's come in the umbrella of couple layer construction. So actually, condensed matter people really love couple layer construction. They give us intuition on, for example, how to build higher dimensional topological phase from lower dimensional ones. For example, we can have some gapless 1D phases, and we take a 1D stack of them, couple them in the bulk, and then gap out excitation such that we are left with, for example, integer or fractional quantum Hall effect. And we have these edge modes that are left on the boundary because we gapped out everything in the bulk. There are similar constructions for taking the Z2 Toric code in 2D, two spatial dimensions, taking a stack of them and condensing excitations, these anyons, in order to form the three-dimensional version. And this will exactly actually be the tensor product construction. And I'll come back to this and how it's related very closely to the tensor product construction. You can also do more exotic couple layers where you can couple different things in different dimensions together to get various fracton phases. And these couple layer constructions actually have close relation to this bulk boundary correspondence. So the data of this bulk topological phase you construct is closely related to the constituents you use, and it appears on the boundary at the end of the day. So this is what I'm going to be using, the couple layer construction, and I'm going to be showing you how it's closely related to these product constructions. So first, I'll need to review what this product construction is doing, and then I'll give you two perspectives on how to think about this product construction. One is from the gauging perspective, and one is from the condensation of anion perspective. And then towards the end, I'll talk about some generalizations beyond the tensor product, for example, to something called the balanced product. I'll briefly comment on that. Okay. Let me begin by first reviewing this tensor product code. And actually, a lot of the work was done in the first talk today, so serendipitously, I'm very thankful to Stefan for covering this ground for me, so I can go through this a bit quicker, and might have more time for discussions. So what is a classical code? For example, you have a 1D Ising model. You can think of this parity matrix formed by just whether you have bits and checks, right? So for example, for the 1D Ising model, this is what this parity check matrix should look like. And abstractly, this parity check matrix is, you can think of it as a map going from bits to checks. And so it's just a map from the set of all bits or qubits and to the set of all z checks. And when we say it's a low density parity check code, it just means this matrix is sparse. So there are finite number of ones in each row in each column. Okay. And for a quantum version, we just have two maps now where we have x checks and z checks. The fact that they commute corresponds to this condition that when you take the parity matrix transpose, and this is 0. And that corresponds to the fact that this is a complex, meaning you take anything from here, you map it twice, it becomes 0. And you should think of this as being analogous to boundary and co-boundary maps of manifolds. So for example, I'm going to be using the cochain complex. It's sort of the reverse of the arrows, which was talked about this morning, where this morning we had faces mapping to the edges, which boundaries, which is edges, mapping to the boundaries, which is vertices. I'm just reversing all that, okay? And so, for example, if you take the chain complex of the 2D, this 2D lattice, right, you can now write down a quantum code where the qubits are living on the edges, the x checks are living on the vertices, z checks are living on the faces. That's nothing but the Toric code, which you are already familiar with. And the fact that these things commute just follow from the fact that this is a complex. Okay. So this is a way to represent a quantum code. Now, if you're given two classical codes, what you can do is you can take a tensor product of chain complexes or cochain complexes and give rise to a new complex. So for example, if I have the repetition code or 1D Ising model, I can have a chain complex where I just map from the vertices to all the two edges adjacent to it, right? And if I take a product of these two, you can think of them as abstractly taking a product of chain complexes. So for example, after you take this tensor product, you will have new vertices which live at the positions of the vertex of one and the vertex of the other, and that's vertex tensor vertex, right? The faces will be where the edges of one code meets the edges of the other code, right? And then there are two types of edges. One is the vertical edges given by this part, vertex tensor edge, and then the horizontal edge, which is edge tensor vertex. So you can see that just taking two classical codes, you can construct a new quantum code given by this length 3 chain complex. Okay, so that's all you need to know for the construction of this tensor product code. Yes?
Is this related to the hypergraph product, or is it a different product?
It's related. The only difference is for the hypergraph product, you actually transpose one of the classical codes. So you change what you meant by edges to vertices and faces, but they're exactly the same in a sense. Okay, and okay, so now that you can actually change this classical code to a good classical LDPC code, and you can get a hypergraph product or a tensor product code with a constant number of logical qubits, for example, but the distance is still square root, for example. Okay. I'm going to stick still with this 1D Ising model. And now I want to show you, if I had 1D Ising models, how do I actually couple them together to create this Toric code or surface code? And that'll bring me to what I'll call the gauging perspective. The reason I'm using the word gauging will become clear later. But actually, I'm going to pivot to something totally different in your mind, might be totally different in your mind. I'm going to talk about a different type of construction with two classical codes, which you might have heard of. And that is called the concatenated code. So what is a concatenated code? You have two codes. And what you do is you first encode in one layer, and then you encode it in another layer. And that creates you, for example, a quantum code. The simplest example is Shor's code, where you take a three qubit repetition code. Let's say the checks are ZZ, right? That's your Z basis Ising model. And you have another code, which is the X basis Ising model. So one of them corrects bit flip noise, and one of them corrects phase flip noise. You encode them in succession, so that you get a quantum code that is robust to both bit and phase flip. Right? So how do we think of this concatenated code in terms of a so-called coupled layer? So this is the construction. So this animation is not supposed to be there. Okay, so you can think of, I first introduce, of course, for source codes, it's 3-qubit, but you can do, of course, maybe in this picture, I'm doing 5-qubit repetition code instead. What you do is you introduce n2 copies, in this case 5, of the outer code, which is a repetition code. So I have 5 repetition codes. And then what you do is to further encode it in this inner code, you notice that each of these has an X logical, which is a string of X. Right? What you do is you replace the checks of this inner code with the logical of the outer code. And then you enforce it. Oops, sorry, animation. You enforce this on every pair. So this X is a string of X, right? And so for this X check, I now replace it with the logical of the outer code. And now I impose this check on every pair of rows. Okay. So when this was 3x3, this was source code, the 9-qubit source code. But now you can do a 5x5 version of it if you want. Okay. So this is, in some sense, coupling these 1D repetition codes together, right? And you can see that, for example, you have a logical, which is given by encoding this twice through the logical of this repetition code, and then this X version of the repetition code. It's this, the X logical is this line here, the Z logical is this one here. But you notice that because this X logical has a good distance, meaning it's long, now this stabilizer we enforced here from the checks of the inner code is long. It's weight 2L. So it actually does not give us a quantum LDPC code. So in terms of the syndrome extraction, this will take a long time, and that's why we might not want to use it in practice. Okay, so now let me pivot back to how this is related to the tensor product code. The idea of the tensor product code is actually we want to enforce this big stabilizer, right? But it's large. So we can use a trick called gauging. And what does gauging do? Suppose when we talk about gauging, we have a global symmetry, and we can promote it to a local symmetry action. This local symmetry action products back to the global symmetry. And we can do that by introducing gauge fields. These gauge fields I'm denoting by adding a qubit for every vertical edge here. And so you notice that if I implement, for example, this 4-body operator, which looks like a plaquette, and I product all of these gauge fields, they cancel, and I reproduce back my long stabilizer. So instead of forcing this large stabilizer directly, by adding these gauge fields, I can break it down into local actions, and enforcing them independently will still give me these large stabilizers back, which is what I want. The caveat is that these local symmetry actions, they don't commute with your original Ising checks in each chain. So what happens is these Ising chains, they're going to get minimally coupled in the gauge theory language. And because there's a gauge field below and above, it's going to gain a Z below and one above, so that it now commutes with your local symmetry action. And now this is exactly the surface code. So you can see that by trying to solve the problem of measuring this large stabilizer, we're naturally led to the surface code, which is exactly the tensor product of these two repetition codes. Yes.
If you have the short code you already have, is it computationally a difficult problem to decide where to put the new qubits, decide how to split the large check, and decide how to augment the...
Right. That's not canonical, but I'm using the fact that the short code is a concatenated code. And then if you gave me this concatenated construction, then there's a natural way to do this. And it's exactly the tensor product, turns out. Yeah. But you need that structure. Otherwise, it's not canonical. Okay. So you can actually, so the nice thing, maybe the summary, is that this tensor product code, you can think of it as solving the problem of these large weight stabilizers. And another nice thing is that, which you obtain by gauging these large stabilizers in the concatenated code. And you might also notice that in the concatenated code, if you swap the rows of which one is outer and which one is inner, you get a different code. It has the same parameters, but for example, if you did the concatenation the opposite direction, you have these large Z stabilizers, but you can also equivalently gauge them, and you actually arrive at the tensor product code. So the tensor product code even also solves the problem of making this concatenation construction, which is not symmetric, symmetric. I just want to point out a very closely related relation to something called the Bacon-Shor code, which is that instead of enforcing these by enforcing this long symmetry by introducing these gauge fields, we could say, oh, let's ignore the gauge fields completely, let me not add them, and I just measure these short local symmetry actions. But now it won't commute with the original Ising checks, and what you arrive at as is the Bacon-Shor code. So in fact, there's a similar construction where you ignore all these gauge fields, and you can construct a subsystem variant of the tensor product code. You can call it subsystem tensor product code if you want, and it has, for example, lower weight, and it's some generalization of the Bacon-Shor code. And actually, this construction is known in the literature. It's constructed by Bacon himself. Okay. Okay. So now that we've done the how I've shown how to think of this couple layer construction for a classical code, now I want to move on to if I do a tensor product of two quantum codes, and I'll connect it to the condensation perspective of topological codes. So now this is more complicated, but suppose I have two quantum codes. This is this length 3 chain complex where I have X checks, qubits, Z checks. I have two of them. I can now tensor them, and I can form this longer chain complex where I have X checks, qubits, and Z checks. The thing on the left and the right, if you remember from this morning, are related to meta checks, but we won't necessarily use that in this construction. And for example, a nice example is if you take the 2D Toric code tensored with the 2D Toric code, then the resulting code is the 4D Toric code. So you can think of starting with a square lattice, you tensor with a square lattice, right? Now you get a hypercubic lattice in 4D. And if you put the edges on the faces, which is degree 2, then that just automatically gives you the loop-only Toric code. And there are formulas for computing what is the number of physical qubits, number of logical qubits, and they're very closely related to algebraic topology because you can capture an example from the Kunis formula. Okay. So we can do a similar construction for the tensor product of quantum codes. Let me just do an example which might be familiar to you from the context of topological phases of matter. So the example is if I take a 2D Toric code and I tensor it with a 1D Ising model, then I can get a 3D Toric code. And there's a related couple layer construction, which is the following, and it was introduced back in these two papers. What you do is you take a stack of 2D Toric codes, and what you do is based on the checks of the 1D Ising model, ZZ, what you're going to do is I'm just going to translate Z into E. And what I'm going to do is I'm going to condense E pairs between every adjacent layer. When we do that, what happens is that now the E in every layer becomes identical because the pair is condensed, right? So an E in one layer can now hop to any other layer. So there's only one E after the condensation. A single M in each layer is confined because it breaks with this condensate. But what happens is the thing that survives is a string of M's going through all the layers, which commutes with this, and that's how we get the M loop. And so this is how we get from the 2D Toric code to the 3D Toric code. And the key is that it's closely related to the 1D Ising model because the thing we condense looks exactly like the checks of the 1D Ising model. So the general idea I'm going to show is that if we have two classical or CSS quantum codes, I'm going to take N2 copies of the first code. So I have a layer. And note that this CSS1 might not be geometrically local anymore. I'm just drawing it as a plane for simplicity. And given the checks of the second code, what we're going to condense is the analog of E and M in each layer. It's going to be like the Toric code, but you notice that these will always braid trivially, because if my Z checks and X checks commute, these E's and these M's will always braid trivially because of the same reason. Okay, and I'm going to show that this resulting condensation exactly reproduces CSS1 tensor CSS2. Okay.
So these checks are non-local?
It can be non-local, yes. So it could be layer 1, layer 100, right? And then in the CSS1, it is also could be non-local itself, right? And it's just the analog of E and M that I'm talking about. Whatever your Z excites and whatever your single X excites. Could be a fracton, could be something more exotic. Okay. So let's do a simple example of a tensor product between two quantum codes. I'm going to get the 2D Toric code, and I'm going to tensor it with the 422 code. So the 422 code has 4 qubits, and it has stabilizers x1, x2, x3, x4, z1, z2, z3, z4. So how does the couple layer construction work? I'm going to start with now 4 Toric codes. So I'm going to have this label I for each Toric code. I goes from 1 to 4. And then there will be some ancillas. These will play the role of the gauge fields I will use later. And it's going to be X at each vertex, Z at each plaquette. And then what I'm going to do now is I'm going to condense. So recall, whenever I see X or Z, I just replace the corresponding thing with E and M. So I'm going to condense 4 E's and 4 M's. So the thing that hops in E is a poly Z. So I'm going to have Z, 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 Z for all the copies of the Toric code. And then the thing on the left and the right, you can think of them as the gauge fields for which I'm sort of using to gauge this one-form symmetry, if you will. And a similar one will be I'll be hopping 4 M's at the same time. So I'll have X, 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 X on each edge. Okay. So you turn on these terms. You can think of adding these terms to the original stabilizer group, which consists of 4 Toric codes and these ancillas. And then now you're left with combinations of terms in the stabilizer group that only commute with the things you turn on. So for example, this vertex term and this single qubit on each vertex gets attached together. That's the thing that commutes with this term, for example. So you're left with this term. And so the final stabilizer group is this. And you can actually check that it has the correct number of logical. So I had 4 Toric codes, and then I condensed away roughly 2 worth of Toric codes. And so you can check that on the torus, this has 2 times 2 number of logicals, so 4 logicals, which is the correct answer. So this is the example. The general construction, let me show you from the chain complex perspective. So recall that we had this more complicated picture of the chain complex. I'm going to gradually build that step by step. So I'm going to start with N2 copies of my original code. So my original code of CSS1 is this A goes to Q, goes to B, right? That's my Toric code. So you can think of that as 4 vertices, 4 edges, 4 plaquettes, right? Where Q is the number of the code 2. And then these maps correspond to the vertex and the stabilizer, the plaquette term of each copy, right? And then what we're going to do is we're going to add an X ancilla. So in this tensor product, there's this combination, this contribution here, which will be extra qubits. That's A1 tensor B2, B1 tensor A2. You can think of them as being the X ancilla and the Z ancilla I add in that construction. These look like this X vertex here and this Z plaquette here. And then what I'm going to do is I'm going to turn on some terms. And these terms are this part and that part of my chain complex. So for example, this contribution here, there is an X check corresponding to each edge, and it maps into, it acts on the 4 edges and also acts on this Z and this plaquette ancilla. And so what it's doing is, for example, we fix Q here, and we're mapping A2 to Q2. That's corresponding to the 4 X's over here. And then there is also a boundary map, a co-boundary map from the edge to plaquette. And so I add an X to each plaquette adjacent to this. And so combined, I'm measuring this operator Similarly, up here, there's going to be a similar term, which is the 4 z's and this 2 z's on the vertex. And what happens is that once I turn on this term, it's going to induce that the product of this plaquette and this ancilla is going to get combined. And in the chain complex language, it corresponds to that. It induces this arrow over here such that this diagram now commutes. So by turning on this term, it induces this one. And so now I have a stabilizer which combines these two together. And that's the only way to make this diagram commute. Similarly, by turning on this term, it induces this arrow such that now this diagram commutes. So now I have the full set of X checks, qubits, and Z checks, which come out. And you can now replace my construction of the Toric code times the 422 code to any CSS code. And the construction is analogous. You would have these degrees of freedom, the original code, some X ancilla, some Z ancilla. You measure the terms corresponding to these maps, they will induce the other terms automatically. Okay. So as an application, let's look at one sort of, the one I mentioned before. Oh, yes, and that's the original, that's the code I mentioned. Let's look at a fun example, which is the one I mentioned before. 2D Tor code, tensor 2D Tor code is 4D Tor code. How do we think about that? So I'm going to have a copy of 2D Tor code for each edge of a square lattice. So each edge, I have a 2D Tor code, right? And then now what I'm going to do is I'm going to condense E and M according to the checks of this 2D Tor code, which means that I'm going to condense 4 M's in every vertex, condense 4 E's in every edge, in every plaquette. If I just told you this at face value, it might not, you might have to stare at a bit, right? That you actually get the 4D Tor code. It doesn't seem very obvious at all, but it just drops out of our formalism. You just do the crank, turn the crank, and this just pops out. So this is sort of a cool application that you can get new sort of couple layer constructions automatically just from this formalism. Okay. So let me just mention some nice generalizations and then conclude. So one thing I was hiding was that if you have longer chain complexes, the actual code you might want to construct has this big grid of stuff. So you might have to introduce more ancillas and measure more terms. There's a systematic way of doing that. And it comes from the fact that you might have these meta checks that was mentioned in these longer chain complexes. Those have to be added actually as extra ancillas if you have any local meta checks to avoid missing some terms in the complex. For example, if I took a 2D Ising model, tensor it with a repetition code, I'm supposed to get a 3D Tor code, but if you do that naively by truncating and forgetting about the meta checks, you might miss some plaquette terms in the 3D Tor code, for example. So we took care of that subtlety there. If you're interested, you can check out our paper. Another nice generalization we did was to get these so-called balanced product codes. And these balanced product codes were used to construct these good quantum LDPC codes with good scaling. And without going into too much detail, what the balanced product does is after you take in this tensor product, you can identify some symmetry, say G, within each code. And what you do is you collapse that. You identify, you make an equivalence class, and you collapse it down into a sort of smaller code. And that's how you get a boost in the distance. And you can think of that as, for example, I'm doing a quotient by some group G. You can think of quotienting only one side of it. And it's sort of, you can think of it as more like a fiber, sort of a stack of CSS1. And then the way, the difference in the condensation is that now instead of condensing just each checks normally, each excitation now gets shifted by the symmetry action, which is the G. So you can think of it like a fiber bundle. If I want to go between each fiber, right, I need some connection to connect between them. And so when I do condense E without this symmetry action, it won't give me the right answer. I have to shift it by an appropriate symmetry action coming from this structure. And it's known that balanced product codes can give you, for example, color code, Haas code, these bicycle, tricycle codes, right? And so And one fun application is similarly to how I mentioned the connection of the tensor product code to concatenated codes and subsystem codes. We can actually even construct concatenated and subsystem versions of the balance product as well due to this deep connection. Okay. So let me just mention some outlook of some forthcoming work we are trying to generalize. This notion of gauging in where I take a bunch of codes, right, and then I gauge some symmetry to break up these little logicals. What I'm doing here is you can think of this condensation as gauging a symmetry, all of the symmetry in each layer, but simultaneously according to the checks of one code. But what you can do is you don't actually need to gauge every single symmetry. You can sort of gauge partially. And this can actually lead to generalizations that go beyond the tensor product code. And actually, this notion of partial gauging has appeared recently in the literature of generalized lattice surgery, where you actually want to partially measure out logicals in your system, but you don't want to measure all the logicals. And so it's a closely connected relation. And so we're using this to get interesting generalizations of, for example, reproduce the X cube, something called the XYZ product, which is a generalization of the Shimon code. And we're also thinking about how to go beyond CSS code. So if you have, I assume that each code in each layer is only X checks and Z checks, but you can have a mixture of them. And for example, we have some example of getting the fermionic Tor code as some interesting balanced product in some sense, where we, instead of quotienting out by translation, we quotient out by the EM duality symmetry of the Tor code, for example. So that's a very interesting construction that I don't fully understand yet, but from a formalism, it just pops out. And then something interesting that might be worth thinking from the condensed matter side is, so far, we've been thinking about a couple of layers just locally, right, to make larger topological phases. But now, because of these quantum LDPC codes, of course, we can just condense layer 1 with layer 100, and we can do whatever you want, right? And as long as it's still k-local. So it'll be interesting to do this for example, non-abelian anion theories, or even chiral ones, right? And see what interesting generalized phases we can come up with these constructions. Okay, so let me conclude here, and thank you for your time.
We have time for a couple questions, please.
Thank you. This was really fun. I'm not super comfortable with the condensed matter language being used. So what would be a good survey introduction for someone working on aircraft codes, but who's not as strong on the condensed matter side? For instance, I don't know the couplet layer construction that you're referring to as very standard in this field.
I guess I would say it's sort of scattered. The one I used mainly was by these authors that I flashed. For example, this is a very nice example that was studied in these two papers. So they study it in the sort of continuum version, but the appendix of our paper also talks about all of these. So also maybe you can check that out as well.
Thank you.
Does this maybe allow you to also construct like defects, different kinds of, say, invertible, not invertible, defects between these, code in itself?
Yeah, that would be interesting. We haven't really thought about that yet, but probably you have to constrain it to certain input codes. Maybe they have to be, the classical code has to be self-dual, right? Yeah, but yeah.
Okay, let's thank Matt again. Go to lunch, everybody. What is that?
That's space paragraph, that point, and also.
I appreciate you.
I am Wilson.